I'm Alex Alvarez.
I'm Jin Park. We're from the Brain Networks Lab at Texas A&M University, and we're presenting Saliency threshold in neurocode and its relation to the power law, Gaussian, and Lambert W function.
Primary visual cortex models that use difference of Gaussian, then Gabor filters, produce neural responses with a power law-like heavy-tailed distribution, even though the image intensity distribution varies widely. Macaque V1 neurons exhibit similar properties. They show sparse, high kurtosis activity. When we compare the power law response with a matched variance Gaussian, they intersect at 2 points. The second intersection point, which we'll call L2, marks where the response becomes heavy-tailed. The central question is whether the intersection point has any functional significance. For example, can L2 represent a meaningful threshold for saliency in neural code?
First, we will talk about power law properties. Li and Choe made the discovery of the power law-like heavy-tailed response property and its functional significance in visual cortical response models. These models produce invariant heavy-tail, power law-like response distribution across diverse images. A is the image itself. B is a response image from the orientation energy model. C is a histogram of the image responses. D is a histogram of the responses from the orientation energy model. And E shows the comparison between a Gaussian and the response histogram from the orientation energy model. Here, Gaussian is a good baseline because when the model is presented with white noise images, the response distribution mimics that of a Gaussian. This provides empirical justification because white noise images do not contain any salient edges. There were three main findings in Li and Choe. Firstly, the response has a parallel-like distribution as we saw earlier. Secondly, when response is compared to a Gaussian distribution with the equal standard deviation, the larger intersection point, which is L2, is linearly correlated with the salient threshold of the response when compared to the human selected threshold, which is on A. Lastly, the L2 intersection point is linearly correlated with the standard deviation of the response, which we can find in plot B. The parallel response we have seen is not limited to the orientation energy model. For example, using GCAL, which is a cortical developmental model, also yielded a parallel-like response in a model trained with natural images. An interesting question is whether modern deep learning vision models such as CNNs exhibit similar responses. By incorporating lateral connections in visual cortex, similar to GCAL model, we were able to elicit a parallel response distribution in a CNN where lateral connections were introduced as recurrent weights. We call this special structure architecture the LC-CNN. As we can see that when the network is untrained or when white noise images are presented to a trained LC-CNN, which is on the left, the response is very Gaussian, regardless the number of the loops. When the natural images are presented to a trained CNN, initially the response is close to Gaussian, but as the loop number increases, it approaches a parallel distribution. You can see loop 4 and 5. And this shows that the orientation model and the biologically inspired GCAL model and the modern CNN produce similar results.
To analyze L2 mathematically, we solve for the point where the power law and the Gaussian intersect. This leads directly to the Lambert W function, defined as the inverse of x times e to the x and satisfying z of w times e to the power of z of w, all equals z. It arises naturally when a variable appears both inside an exponential and as an algebraic term. Using Lambert W, we obtain a closed form solution for L2, where C is a normalized constant, A is the power law exponent, and sigma is standard deviation. It's interesting to note that Lambert W function is another fundamental function that frequently appears in natural and engineered systems. These results reveal a mathematical connection linking the Gaussian baseline, the power law response, and the Lambert W function. The Gaussian provides the baseline response to white noise. The power law defines the saliency threshold structure seen in natural images, and the Lambert W function provides the analytical bridge between the two. Together, they suggest a deep underlying structure governing how neural systems establish response thresholds.